I'm part of the faculty of the Department of Mathematics, and I recently wrote a book about SciPy. And the title of the book is Learning SciPy for Numerical and Scientific Computing. And the reason I wrote it is I was using SciPy, and out there were lots of tutorials. I could go online and look for a function that I knew that I wanted to use, and look at the usage, right? And they will come up with like a couple of nice examples, but the examples were, you know, like random examples. You know, you have to optimize this function, bring a function, you know, optimize it. But there was no context. I did not see a context. So I'm okay with that because I'm familiar with the whole environment, but I felt that there will be people out there that will want to use SciPy for their normal things, but they will be missing the point. So what I did is I wrote a book where I sort of explain SciPy from the point of view of scientific computing, which is where you want to use it, and then give examples which are meaningful, okay? And by the way, this is the last time I talk about my book. That's not what I want to talk about. Just buy it and make me happy. Let's see more hands. Have you used SciPy before? Raise hands. Oh boy. Well, that's okay. I hope you will be using SciPy after this. So what I want to do is I don't want to flat you with lots of examples. I'm just going to do one example, and that's going to be enough. But before I give you that example, I want to sort of like tell you why you want to use SciPy for this example, why it makes sense. All right? And that's going to be like the first part of my talk. And why it makes sense is because SciPy is designed for scientific computing. Are you familiar with the term scientific computing? You guys know what it is? Do you know the basic principles of scientific computing? All right, well, let me tell you what it is. Scientific computing is concerned with constructing mathematical models and quantitative analysis techniques and using computers to analyze and solve scientific problems. Think of the example that Phil gave us before, weather prediction. Okay? You cannot test that in a lab. You have to write a model in a computer, hopefully a big gun, right? And then analyze what this, the output of this code is telling you. Okay? That is scientific computing. And if you want to be successful in scientific computing, you need to follow several basic principles. Okay? And let me explain you about these principles. When I was an undergrad, when I finished my degree, I was fortunate enough to be invited to help in a big conference. Okay? I was a pure mathematician. I had seen no applications whatsoever. Everything was very abstract for me. Do you understand where I'm coming from? Everything was rings and ideals and derivatives, but I had never seen an application. So I was invited to this big conference, international conference. Anybody that was part of this algebraic geometry environment was coming to Madrid in Spain for about 8 days. I mean, everybody, Americans, English, Russians, French, German, whatever, you name it, it was there, right? And we had divided this conference into several topics. Each topic had 1 or 2 rooms, and we were assigned to help the organizers of each room. Are you following me? Okay. So naturally, you wanted to be assigned to a room with where there will be scientists in your area, so you could talk to them, maybe score like a postdoc or something, right? And also, you also wanted to work in those rooms because pure mathematicians, they only need like a big blackboard, lots of chalk, and they deliver the, does that make sense? All right, so as I was the new guy, I got assigned to the applied mathematicians. Okay, those were a pain in the neck because they all bring their own device, they all want their cables to connect with the computer, and frankly, I had no interest in that topic, and applied mathematics, what was that? So I was kind of frustrated. Anyway, so I started helping these people, and I was sitting there in one of the talks, and this talk was amazing. It was an eye-opener. It had 2 parts. In the first part, this gentleman, I think he was French, working for the equivalent of the Department of Energy in France, was showing us how you can use all these high-level mathematics that you learn in masters and PhDs to solve the following problem. You have a bunch of Lego pieces that you code somehow, and then you have a target construction. Okay, the target construction is just a shape. It's not given like how the pieces are going to be there, right? And then using this, again, high-level mathematics, the guys have developed a way to sort of like grab a piece and decide if it's going to be used or not. If it's not going to be used, you throw it. If it's going to be used, it rotates the piece in space, shifts the piece in, for a few inches and places it somewhere, and then grabs another one with the same. I'm going to use it, yes or no? No, throw it, yes. Shift, rotate, shift, and put it there, and they were like nice. They would click and everything. But the point was, they had modeled a real life situation to something that I could understand. I was very happy about the fact that I could see all those rings and fields and toric varieties and all those things that sound weird to you, but to me they made sense, and it made sense how to bring those two things together. And that was only the first part. At that point, I was amused. But the second part of that talk, they said, okay, so we have a similar problem. We have a big power plant, okay? And instead of Lego pieces, we have resources like people, cranes, mortar, bolts, whatever, you name it, okay? And what we want to do is the following. Imagine that this room is the power plant, and over that corner we have some kind of radioactive material, right, that we need to change because it's losing its power, right? And out there we have another one, right? We want to change that. And we want to do that change as fast as possible, as safe as possible for our employees, and as cheap as possible, okay? So they have designed an AI, artificial intelligence, environment to code that program as if it were Lego pieces and look for a solution, okay? And they found, the program found an amazing solution. The program said, open that window, make a temporary second floor, the radioactive material outside is going to go through that second floor, the radioactive material inside is going to go through the first floor, drop it, grab it, throw it, get rid of the second floor, you're good to go. A program did that. Nobody, no human was involved into that solution. At that point, I was not amused anymore. I was sold. Are you feeling it? That was amazing. So I talked to my professors and said, okay, I'm done with all this pure mathematics. I want to see what I can do. So we had enough resources to send me here and there. So by the way, that shows you the very first principle of in scientific computing. You need to trust the mathematicians. They have all these techniques, even if you don't understand them. They have all these techniques that will make your problem a bliss. It will solve your problem with no effort. Am I making sense? So anyway, so they sent me to this conference. You guys familiar with Mandelbrot? You guys know who Mandelbrot is? Right? The father of fractals. He passed away recently. Anyway, so he was coming to town, and I said I want to meet him. They took me to this conference, and he was a mathematician. The topic of the talk was mathematics. It was called multifractals. And when I arrived in Cambridge for this talk, there were about 200 people, 6 mathematicians. Only 6 mathematicians. I was one of those, the 6. The rest were engineers, biologists, chemists, computer scientists, and they all had similar problems they were working with. The common topic was this multifractal, and they all had different techniques that they were using to approach these problems. Some of them were exclusively using statistics and probability or data mining, you name it. Some of them were using optimization techniques, gradient descent, whatever you name it. Some of them were using exclusively partial differential equations, the numerical version. But they all have this common ground, this multifractal new technique that this mathematician was developing, and it was sort of like the glue, right? By the way, they all hated each other. It was all the talks were a lot of fun because there were lots of fights. But anyway, the point is, at the end of the talks, even though there were some fights in the rooms, these guys will get together and try to combine their different techniques to arrive to better solutions to their problems, right? That's the second principle. You need to trust all these other people, okay? They all offer something to you in the same way that you offer something to them, okay? I will cut the story short because we don't have much time. The third principle is you do need to trust the computer scientist. This is the key of scientific computing. You do not want to write your code from scratch. You do not. Computer scientists have a big knowledge of not only the computers, that's not the thing, they have a big knowledge of all the different structures that you can use in your codes, in your algorithms, and how to access them faster, all right? If you're going to use a function, what's going to work and not. They have all these knowledge that you do not have, that I do not have. And I will leave that part of my research to them. Okay? You do need to trust them. Or, if you have a library like SciPy, explore the SciPy library to see if there's already a function in there that solves your problem. That's very important. That's one of the points of SciPy. It does have everything for you already, even if you don't know it. The fourth big principle is now you and I have to communicate, okay? And this is very common. You are a physicist, you have this problem, you explain it to me in plain English, and I may understand part of it or all of it. And then I sit down and write some code, write some algorithm, and send it back to you. That is the communication that we need to be very clear. The person that receives my algorithm should look at the algorithm and understand or realize that whatever this person told me, it's exactly what it says in this algorithm, right? So you don't want to spend hours decoding all these for loops, and you don't want to spend any time looking at low-level code. Am I making sense? You want to see the code and be able to read it and interpret that as, yes, this was my idea, okay? And finally, the fifth and last principle is big guys. Most of these problems, if you do not have one of these resources that we're offering here, you're dead. You cannot do most of the things with your laptop. It will take you years to do what one of these machines can do in 30 minutes. So far, so good? All right. So keep in mind these five basic principles, because this is going to justify my use of SciPy. But SciPy is not the only one that you want to use. If you're going to work, it's certainly the one of the methods that I trust most, but it's not the only one. If you want to work in scientific computing, your resources need, first, these two optimized algebra libraries. You need BLAS and LAPA. Even if you haven't heard of them, they are always there. These two guys are the ones that will carry most of the computations. Okay? Talk to your computer scientist. And then you have two options. You can do your coding that you don't touch. Okay? Those libraries you do not touch. Then you can do your coding through a computer algebra system. Okay? And there are more than these four, but I chose those four because they are the ones I'm most familiar with. MATLAB, certainly everybody has used it. It is amazing. Right? Very easy to code. Amazing graphing capabilities. However, you've got to pay for it. And if you want to change something on it, you have to request it and wait for the change in the new release. And so, you are not very MATLAB is not very flexible in that sense. And sometimes I want to access a specific function and change something on it. Okay? Mathematica, Scilab. Octave is very similar to MATLAB. Octave is free, so it's a good way to go about it. A problem with computer algebra systems is unless they on purpose find a way to communicate or to make these systems communicate with something else, you're SOL. You just can't. You have to request things. So what you want to do instead is you want to use a computer language that has capabilities of doing scientific computing. Okay? And C and Fortran, they're always there because BLAS and LAPACK are written especially for these two. And C and Fortran right now, they are the ones that carry the heavy duty, the most intensive calculations for you. You cannot escape it. But it doesn't matter if you don't understand C or Fortran. One of these other computer languages is going to help you interact with those. Perl is surprisingly is very, very powerful, but not just Perl by itself. You need the PDL, Perl Data Library. Okay? It has amazing computational functions and graphing capabilities. R, are you familiar with R? If you're into statistics, data mining, data analysis, R is very powerful. Again, it has by itself interesting graphing capability too. This one is new, it's relatively new. I think it's like a year old. I've been toying around with it for a few months and everybody very satisfied. And everybody says that Julia is the language that is going to make R obsolete. But let's see. Okay? And finally, we have Python. Python is amazing. Not by itself for scientific computing. What you need is what we call PyLab. You need to combine the power of IPython, that Phil was commenting before, with the libraries NumPy and SciPy that Ben was commenting before, and with Matplotlib. Okay, for the graphic part of it. Okay, it is not the only way to go about it, but it's certainly the basic way to go about it if you want to do scientific computing. And Ben gave us a very nice example with 4 columns of all the other, let's say, libraries that you can use to sort of like work in this area. The ones that I use most often are Scikits and Pandas. Pandas is for data analysis, and Scikits, Ben showed us Scikits for learning,
machine learning and image processing.
For image, but you have Scikits for astronomy, for medical imaging, for speech, everything that you can imagine. Okay, just go look for scikits.org, I think, and you will see how many different libraries you have that maybe are already solving some of the problems that you have. Okay, trust the computer scientist. Okay? And I could go on and on and on because there's so many resources for Python. It's ridiculous. All right. Let's see what's next. So let me tell you, let's go now into SciPy itself, now that I have sort of like justified why I want to use SciPy. So you can see these before. This is what I call, what we call a mind map of the different areas of mathematics. And remember the first basic principle, trust the mathematician, because this person knows a way to solve your problem very easily. All right? Trust the mathematician. So SciPy is going to mimic the different areas of mathematics. So if you're working with an algebraist, the only thing that you have to do is access whatever SciPy has in this area, the algebra. And can you read it? I'm not sure you can read it very well. Is it readable? There's lots of information there. Basically, what we have the area of algebra, analysis, combinatorics, and geometry. That's for pure mathematics. And then applied mathematics has like a couple of extra areas that are basically a combination of all those sub areas that you have over there. Okay. In algebra, what we have, for example, if you're going to use big matrices for your problem, you want to treat those matrices with linear algebra techniques. Okay. Or if you are not interested in the structure of the matrices and solving and taking determinants, you are only interested in counting things that happen in those matrices, and your combinatorics is going to take over. Okay? if you're working with differential equations, ordinary differential equations or partial differential equations, and you're doing some optimization, finding maxima, minima, roots, and then you're going to do things with analysis. And if you have triangulations, you're working on something that represents terrain or clouds or whatever, you want to use the geometry part of the mathematics. Am I making sense? Okay. Well, SciPy mimics all this. For example, here in pure mathematics, I forgot to, on purpose, to talk about the foundational mathematics, logic and set theory. Those will be here. Okay. You have, in the SciPy library, there are two modules, miscellaneous and constants, that take care of that basic part. You do not want to say, every time you're going to use pi, define pi as 3.1415, oh, what was the fourth one? You know what I mean? They're already there, and they're optimal. The definitions are optimal for your architecture. Do not touch them, use those ones. Okay? There's another example. So I have a marker. Here in miscellaneous, if you are ever going to use in your computations the natural logarithm of 1 plus a value, everybody understands what the natural logarithm is? You do not want to code it like this. Bad. Your advisor will hang you from your thumbs or something. Bad. You do not want to use it like this. In MISC, you have log 1p that takes care of the weird examples where the x, for example, is very small or very large. Does it make sense? Trust the computer scientist. What is the distance between the points x1, y1, and x2, y2? Everybody knows that, right? The distance is the square root of x1 minus x2 squared plus y2 minus y1 squared. Well, we could code that. SQRT, open parentheses, back. Do not use that. Don't do it. Because if what you have inside is very large or very small, this is not going to be accurate. It's going to give you an error, then it's going to spread all over your calculations. Instead, in miscellaneous, you have a norm function that will do that for you and will take care of those weird examples. Am I making sense? That's why you have to trust SciPy better than yourself. Yeah, let me go down. If you're going to do something that requires matrices or polynomials, you want to use the modules that SciPy and NumPy have exactly for that. Do not write them yourself from scratch. Okay? If your matrix is a triangular matrix or a sparse matrix, then SciPy has special functions that deal with those cases, right? Rather than using a black box solver, you want to use whatever SciPy has for you for that specific case. If you need to integrate functions, look for maxima and minima, interpolate, then you want to use these three modules: integrate, optimize, and interpolate. The first module, special, is very important too. There are so many functions already that are special that you want to use. If you have a system of differential equations that you need to solve and use the solution, well, SciPy has already done that for you. Just look for that system of differential equations. Oh, here it is. Let's use the solutions that somebody else have computed for me, rather than me doing it from scratch. Okay? So it's very powerful. The typical example is, have you ever used a computer to calculate the factorial of a number? Right? So you will go, oh, the factorial is just n minus 1, n minus 2, and so on, right? Do not code it like that. It's just a waste of time. Especially if you're going to do things on the form n factorial over n factorial, do not use that way to approaching that and you're going to be wasting resources and your time. What you want to do instead is, there's a function, special function called gamma, and that is already coded like that. It computes factorial in a different way as an integral. Let's see, I can remember something like this. Probably my student over there can tell me better. And this integral is going to give you a much faster and resource optimized way to compute those factorials. And you're going to be able to do many things with those that otherwise will be very, very expensive. Okay. Making sense? All right. In the combinatorics part, we have cluster and sparse CS graphs if you're going to use graph theory. In the geometry part, we have spatial and ODR. ODR stands for orthogonal distance regression. So you can explore the geometric properties of some of your objects through SciPy. And then there are things that don't fit here in any of these 5 because they actually use some of these at the same time. For example, if you're going to do signal processing or image processing, you want to use the utilities in these 2 modules. If you're going to do statistics and probabilities, you're going to use the functions in these 2 modules. Okay? Does that make sense? This is why SciPy is so good at what it does. Because it mimics what the mathematician will do. Right? And I guess it's time for the example. How much more time do I have?
We can run over a little, so it's okay. If you'd like me to leave, that's fine.
All right. Well, let's go with the example. Now that you have basic principles on how SciPy works and why SciPy will work, I'm going to give you a very fast example. This image that you see over here, it's some kind of catalyst, NB4W13047, some kind of oxide. And what we want to do with this is, you see all of these white dots are atoms, actually columns of atoms, but think of them as atoms. Right? Black means there's a hole there, there's a gap. Okay? And what you want to do, without having a grad student do this for you, is count how many atoms you have and how they relate to each other. You want a computer to do this for you. Am I making sense? And maybe explore that structure to whatever create a new one that will do the same as this one, whatever you want to do with it. Anyway, so I'm going to show you a very naive approach to solving this problem. Okay, to extracting this structure of the model. So what you're going to do is, in the first step, is you're going to segment all the atoms, differentiate them from the gap, right? That's what you want to do in the first step. How would you do it at this point? You know? I'm going to use a technique, it's called thresholding. Because you see, in my image, it was black and white, remember? Blacks are zeros. The brightest white is 1, and everything in between is a number between 0 and 1, right? And what we know is, because the image was taken with a STEM, scanning transmission electron, the intensity in the image tells me what kind of atom I have. It tells me whether I have niobium, or if I have iron, if I have oxygen. Does that make sense? So what I want to do is take that information and say, well, if I want to segment all the atoms that are heavier than iron, then I'm going to look for a threshold, let's say 0.7, and look at all the parts of the image that have a higher value of 0.7. Right? That's thresholding. And it gives you a pretty good map of where all those atoms are. Right? But this is just a black and white picture with some blacks and whites. Right? What I want to do next is I want to label each of these guys with a different number so I can count them, differentiate them. And before that, maybe I should realize that There's some of those that are very, very small. I don't care about those ones, because if they're very small, they're likely not atoms, they're likely noise. So I want to erase those guys from my image. Making sense? So anyway, so I will get rid of those and then label each of those atoms. How would you do that with a computer? You think it's easy? How many lines of code do you think you will have to write to get that done? Now I have labeled all the atoms. I know how many they are. What I want to do at that point is I want to compute the center of mass of all those blocks, of all those atoms, to see where they are and report them. Okay? And you will get like a map like this. So like two different ones for two different set of atoms. And I want them less here and more there, but you have an idea of what we're looking for. Does that make sense? All right? And finally, to report the structure of this outside, what you want to do is give a Voronoi diagram of that lattice of points. Are you familiar with the term Voronoi diagram? You guys know what it is? No? Let me explain it real quick. You're in your car. That's the eraser. You're here in your car, and you're out of gas. And you ask your GPS what's the closest gas station, right? So let's say there's like gas stations over here, over here, over here, over here. So forget about the car now. A Voronoi diagram is a way to divide the plane, this map, into regions, and each region is going to report which point is closer to one of these gas stations. So for example, in these 2 points, I make this line. You see how any point here is going to be closer here, and you want any point here is going to be closer here. You see? We're going to do the same here. Okay, we're going to do the same here. We're going to do the same here, and then they're going to meet somewhere here. I don't know how exactly. It's something like this. Okay, so this is a Voronoi diagram of these 4 locations. They look really pretty, right? So when you're out of gas and you ask your GPS to locate the closest gas station, your GPS locates those gas stations, computes a Voronoi diagram, finds in which of these regions you are, and then says, go to this one. Okay, that's the way it does it. It's very fast. Okay? This is a Voronoi diagram for 4 locations. This is a Voronoi diagram for 2,000 and so on locations. But as you can see, this Voronoi diagram gives you the structure that I was looking for, and it's very easy to interpret. Okay? How many lines of code do you think you have to spend to do these? How many resources? Any guess? Any wild guess? 20. Actually 13. With SciPy. And most of them are garbage. Like for example, the first 4 lines is a preamble that says, I want to use NumPy, I want to use SciPy, and from SciPy, I want to use some functions in the image processing module. The ones that I want to use are binary opening to get rid of the small atoms that are actually not atoms, label to label all these atoms, like put a number to each of them, center of mass to compute the center of mass of those atoms, and distance transform PDT to find that Voronoi diagram, preamble. Okay, we're going to use again to cover this. Computer science is working for you. Then you load the image and you say, for example, img equals, and you read the image, it has capabilities to do that. And once you have the image, you want to do the threshold. And with SciPy, doing the threshold is very easy. You don't have to code anything fancy. You just say BW atoms is black and white atoms. Remember how we had a black and white picture? It's going to be all the pixels in my image which has an intensity greater than 0.62. And I got this 0.62 just from observation and because that I knew what atoms I wanted. You see how easy it is to code this with Python? Now you want to get rid of the outliers, those ones. So you say I'm going to change my WB atoms, my black and white atoms, to the same thing that I had before, but I'm going to eliminate all those little ones using binary openings, And what I want to eliminate is a 2x2 matrix of ones, like 2x2 atoms or something smaller. Does that make sense? It does that for you. You don't have to code it. Next step is you want to label all those atoms. Okay? Text to lines, but basically what you get is with the function label, with the black and white atoms that you have, and one structural element that will tell you whether you want certain cases to be together as one atom or two atoms. You just compute it like this, and it will give you all the different atoms labeled 1, 2, 3, 4, 5, 6, 7, 2000, and how many you have. All right? You compute the centers of mass of all those labels using this very easy function called center of mass. This is the image you have, the segmentation, the labels that you have, and then you have to specify how many you want. And then you collect the x coordinates and the y coordinates. See how easy? And finally, you just compute the Voronoi diagram by using distance transform ET on the data that you have. And that's it. Okay? And look at how we went over it. You gave me a problem. You said, I want the structure, the structure of this molecule, okay, as a biologist or whatever. And I, as a mathematician, explained to you the way you're going to do it. You're going to threshold, you're going to take care of this, you're going to find centers of mass, you're going to find a Voronoi diagram. And I explained very briefly what those things were, right? And then we gave this to the computer scientist, and in 20 lines, using that algorithm that I told you, just came out with a solution. Okay? It might take longer or shorter depending on your machine, but that's about it. Okay? I hope this example suffices, and you're happy with it, and you start using SciPy. If you want more information and if you want to see more examples and things like that, I have a very active blog, blancosilva.wordpress.com, and of course my book, and I guess that's it. Thank you very much.
Thank you, Francisco. So I guess the bottom line for me is don't reinvent the wheel.